Hello and welcome to chemistry. So what we're talking about today is we're continuing the discussion of compounds and how we identify them. We talked a little bit about the naming and the formulas of things made of one element, things made up of two elements, whether they were ionic or covalently bonded. What we need to talk about next are polyatomic ions and how they form into the mix. Now, there's different kinds of polyatomic ions. Polyatomic, not surprisingly, means many atoms combined together to form a single ion. So yes, we could have, for example, a fluoride ion where we have a monatomic species, a single atom of fluorine with a charge on it that makes it an ion. But we can also form ions by covalently bonding many atoms together and putting a charge on the net result. One way to think about these polyatomic ions forming that will help you with the formulas and the naming of them is to see these polyatomic ions, or at least the ones of the nonmetals, as being the monatomic species of that nonmetal with oxygen dogpiling on top of it. For example, if I had a phosphide ion, that necessarily or most likely has a 3- charge on it. If that phosphide ion is around a bunch of elemental oxygen, neutral oxygen, well, oxygen likes electrons. It's going to dogpile on phosphide. It's going to reach out to grab that extra electric charge. But phosphorus is a nonmetal. It's not going to give up its electrons the way a metal might. And so they lock together. And when one oxygen adds onto it, now you have a diatomic species, the phosphide ion and a neutral oxygen. In other words, PO3-. Then another one comes along, and now you have PO2, still 3-. Put a third one on, PO3, 3 oxygens dogpiled on phosphorus, still a 3- charge on it. You can even get a fourth one, put a fourth oxygen on there, still a 3- charge on that phosphide ion, now with 4 oxygens layered around it. If you see many of the polyatomic ions as being this situation, an underlying monatomic ion that then gets oxygens layered on top of it, it'll be easy to always predict the charge for that polyatomic ion, because in most cases it's just the charge of the underlying monatomic ion. Phosphide ion has the charge of 3-, and therefore the polyatomic ions, the oxyions of phosphorus, also have a 3-. Sulfur has a 2-, sulfide, and therefore the oxyions of sulfur also a 2-. Chlorine, bromine, iodide all have a 1-, and yeah, their oxyions all have a 1- charge. Now, carbon is a more complicated story, and we'll get into carbon in more detail in the future, but carbon is little brother nitrogen. These two don't behave the same way. Carbon, you might expect to have a 4+ or a 4- charge on the monatomic species. The oxyion, the polyatomic, has a 2-. And for nitrogen, you might expect a 3-, but it's a 1-. So nitrogen and carbon, the charge you have to remember is different than that pattern. But for most of the polyatomic ions you're going to look at, most of the oxyions, it's just that underlying monatomic species with some number of oxygens stacked on it. Now, the bigger atoms, the atoms made from the elements phosphorus and sulfur, which, by the way, are also the polyatomic elements, the phosphorus and sulfur, that can handle 3 or 4 oxygens easily. And the most common oxyions you will run into from sulfur or phosphorus have either 3 or 4 oxygens on it. The rest, the cutoff's at 2 or 3. Carbon, nitrogen, chlorine, bromine, iodide, the dividing line is between 2 or 3 oxygens. That's the most common ones you're going to run into. Now, in each case, the larger one, the one that has, for phosphorus, 4 oxygens, or for carbon, 3 oxygens, the one that can hold more oxygens, that's the 8 ion. The way I remember that is Thanksgiving. I ate more. As a result, the one that has more oxygens is the 8 ion. That's why the carbonate ion is CO3 2 minus. Nitrogen, it's NO3 1 minus. And for phosphorus, again, phosphorus and sulfur can handle a few more. The bigger one is PO4 3 minus and SO4 2 minus. That's the 8th ion. Now, the smaller of the two is the ite ion. Ite is smaller, mites are smaller. And so, for example, if I have the sulfite ion, well, that's the smaller, and it's 3 or 4, so that's a 3, so SO3 2 minus. For nitrogen, it's NO2, 1 minus is the nitrite ion. The sulfite ion, carbonite ion, chlorite ion, the smaller of the two is the ite. So 8th and ite, big and small. And as long as you remember the charge on it, you should have no trouble taking the name and making the formula, or going from that formula to make the name. Now, there are a few exceptions to that rule. For example, you can have bigger than the biggest, and you can have smaller than the smallest. You will usually run into these in the form of the halogen oxyions. For example, the biggest ion for chlorate is CL23 1 minus, the chlorate ion. That's the big one. But you're going to have bigger than the biggest. You can supersize that biggest. It's still a chlorate ion, but it's a supersized one. It's the perchlorate ion. You can also have a perbromate and a periodate ion. Notice fluorine isn't in there. You're never going to have a fluorate ion or a perfluorate ion, because oxygen doesn't dogpile on fluorine. Fluorine's the tougher one. If anything, he'll dogpile on oxygen. So fluorine isn't part of this mix. Anyway, the biggest one is the bromate ion. And bigger than the biggest is the supersized one, the perbromate. And you can have smaller than the smallest. The smallest one is the bromite ion, BrO2 1 minus. But you can have Br with a single oxygen 1 minus. Smaller than the smallest? Smallest thing I've ever seen is the tip of a hypodermic needle. You ever look closely at those things? Man, needles scare me. But if you ever look closely at those things, the tip of that is vanishingly small. Smaller than the mite is the hypobromite ion. Hypobromite, hypochlorite, hypoiodite, all of these are smaller. They're still ite, but they are smaller than the smallest. Each of these has 1 oxygen, and the hypobromite, for example, is BrO, single oxygen, 1 minus. There's also a few polyatomic ions that don't fit this pattern that you are responsible for, you are going to need. One of them is the ammonium ion. Ammonia is NH3. It's a neutral compound. But if you slap an H plus on it, then you get 1 more hydrogen and a positive charge. And this forms the only polyatomic cation you will be responsible for. NH4 1 plus. We're going to need that for a bunch of examples as we go forward. Another one is the hydroxide ion. Hydroxide you may already know. OH 1 minus. It's basically water where you pulled off an H plus. What's left is OH 1 minus, and this is the hydroxide ion. We're definitely going to need that. You'll also need the cyanide ion, CN 1 minus. You will additionally need the acetate ion. Okay, the acetate ion is an organic ion. The acetate ion has got 2 carbons. It's got 3 hydrogens, 2 oxygens, and a 1 minus on it. It's a big thing to write. And you can write the full acetate formula, either showing connectivity or not. It will be accepted. It's fine to do it that way. But me, I wouldn't do it that way if I were you. It's kind of asking for trouble. There's a shortcut. You can abbreviate the acetate residue or the acetyl residue as A lowercase c, and then just put the oxygen on it. A lowercase c, oxygen 1 minus. Now be careful, that's not the element actinium, which has that same symbol. This is this is organic shorthand for the acetyl residue on an oxygen. In other words, the acetate ion. You don't need to know all the details on that. You do need to know you can legitimately write the acetate ion as capital A, lowercase c, capital O, 1 minus. And I encourage you to do it that way. Everyone's going to accept it, and you're less likely to make a typo. And the details of that you will learn about in a future class. But for now, it's a quick and easy shortcut. All right, these are the polyatomic ions. These are the ones you're responsible for. And you can use flashcards to memorize them all. There's also some polyatomic ions of metals we're not going to get into. But you can, instead of just memorizing, you can recognize these patterns and you can read the name and the formula right off the board. All right. Next up we can do we can make compounds with these oxyions. In the same way we made binary compounds from monatomic ions, we can make pseudo-binary compounds using these polyatomic ions, just treating them as if they were monatomic and applying all the rules you already know. Now, for example, when you named lithium chloride, you just took the lithium ion and the chloride ion, slapped them together, and you got lithium chloride. You can do the same thing with the polyatomic ions. Instead of chloride, just use, for example, the nitrate ion. So take the nitrate ion, the lithium ion, slap them together, lose the words ion, and you have lithium nitrate. And in this way, you name the pseudo-binary compound of lithium ion and nitrate ion. Now, all the same rules apply, so if you have ambiguity in the cation, like in case of iron, where you have both the ferrous and the ferric, the iron 2 and the iron 3 ion, and you combined it with chloride, then it became iron 2 chloride or iron 3 chloride. If you're doing that with nitrate, you got to remember to use those symbols as well. Iron 3 nitrate or iron 2 nitrate. You can also say ferrous or ferric nitrate. And yes, that ammonium ion is the only cation, and you can use it in this way. Instead of replacing the chloride, replace the lithium with ammonium ion and chloride ion. Bring it together. That gives you ammonium chloride. Okay, we can play with these a little bit. That first ion up there, do you know what that one's called? That's CO3 2-. Okay, the underlying element is carbons, and 3, is that the big or the little one for carbon? Most of the non-metals, it's 2 or 3. 3 is the big one, therefore that is the carbonate ion. If you look at the next one, that's sulfur. SO3 2-, looks similar to the one above it, but remember, sulfur and phosphorus are the bigger ones. They can do 4 or 3. So for sulfur, the 3 is the little one. What's the little one called? Right, the little one is the sulfite ion. The one underneath that, NO3 1-. Okay, again, 2 and 3 for most elements, 3 is the big one, and I8 more, nitrogen underneath, this is the nitrate ion. And if I take the nitrate ion and I combine it with a metal ion like lithium to produce a neutral compound, that neutral compound is then lithium nitrate. If I take magnesium and I combine it with the CO2-, which one was that? CO2-? CO2- would be the smaller one, 2 or 3. Most elements, the smaller one has got 2 oxygens. That's the carbonate ion, magnesium carbonate. If I take magnesium and I add 2 nitrites to it, remember, the nitrite has a 1- charge, the magnesium is a 2+. Hey, what do you think I'm going to call that one? Be careful. Doesn't matter that there are 2 nitrites, right? There will always be 2 nitrites because magnesium has a predictable charge. So does nitrite. So we don't call this magnesium dinitrite. It's just magnesium. It's just magnesium nitrite. And it would be wrong if you said magnesium 2 nitrite or if you said magnesium dinitrite. Never over specify. All right, how about that CN1 minus ion? You remember what that was called? That's the Johnny Appleseed ion. That's the cyanide ion. Calcium with 2 cyanide ions, what do you think we call that? Correct. Just calcium cyanide, not dicyanide, because the charges are predictable. Then we've got K. Remember which element that is? Right? The old name was calcium. The modern name is potassium. So we're going to say potassium and then BrO31 minus. Big one, a little one. 3 is the bigger one. That's the bromate ion. So potassium bromate. Now I got BrO4. Wait, the biggest one was 3, so this is bigger than the biggest. Bigger than the biggest is still a bromate, but it's a supersized one. What do I call this? Well, I'm bringing together the potassium ion and the perbromate ion. So now I have potassium perbromate. And that one on the bottom, man, that looks so complicated, doesn't it? 3 NH4s and a PO4, but again, just treat it as if it was a binary compound. If you got 3 of one and 1 of the other, and the charge is all known, just name the first one, name the last one, stick them together. The name of that isn't that hard. Ammonium ion, phosphate ion, that's ammonium phosphate. All right. Now, if we need to go in the other direction, for example, calcium sulfate, well, just name the 2 ions. Okay, calcium ion, how do we represent that? It's in column 2. So the symbol for calcium is C lowercase a 2 plus. And the sulfate, sulfur with some oxygens on it. 8 is the big one. How many oxygens on the big sulfur? Right, sulfur is 3 or 4, so that's 4. So SO4, and the charge on it 2 minus, because sulfur's got a 2 minus. Calcium 2 plus, SO4 2 minus, just slap them together, and you got calcium sulfate, CaSO4. Lithium sulfite, sulfite is the smaller one, so that's SO3, still 2 minus because it's still sulfur. And I'm going to stick lithium on it. What's the charge on lithium? 1 plus. Note, 1 plus, 2 minus. To balance it out, I'm going to need 2 of those lithiums. So my formula then becomes here we go. My formula is Li2SO3. All right, the next one is potassium nitrate. Nitrate, bigger one or the little one? 8 is bigger, right? Nitrogen's one of the common elements, 2 or 3. Bigger one is 3 oxygens. But what's the charge on the nitrate ion? That's a special one, you got to remember it. Nitrogen breaks the rule. It's not 3 minus, it's 1 minus. That's NO3, 1 minus. If I team it up with potassium, which forms a +1, I can just slap the 2 together, KNO3. Magnesium nitrite, the neutral compound. Well, magnesium's got a 2 plus charge. So I'm going to need 2 of those nitrite ions to balance it out. Name is still magnesium nitrite. But when I write the formula, I got to show 2. So what is that? KNO3, 2? Be careful, that might look like 32. So let's use parentheses. K, open, or magnesium, sorry, Mg, open parentheses, NO3, close parentheses. Now slap the 2 on it. Okay, if you got something like iron 2 carbonate, iron 2, well, the charge is just 2 plus. Iron, of course, is one of the old elements, so Fe. Fe 2 plus, carbonate, CO3 2 minus, slap them together, and you got Fe CO3. If I did instead of the ferrous ion, the iron 2 ion, if I did the ferric ion, the iron 3 ion, Now I got a 3 plus charge and a 2 minus charge. It's getting a little more complicated, but remember, it has to cancel out. Look for the smallest whole number multiple of 3 and 2, 6. If I want to get a 6 plus and a 6 minus, well, if my iron is a 3 plus, I'm going to need 2 of those, and if my carbonate is a 2 minus to get 6, I'm going to need 3 of those. So Fe2, CO3, and make sure you put that CO3 in parentheses so someone doesn't think you've got 33 oxygens there. How about cupric bromate? How does that one going to work? Okay, cupric. Remember, copper and mercury are the one-off elements. They can have a +1 or a +2 charge. The ick is the bigger one. 2 is company, 3 is a crowd. 3 is the bigger one. So if copper has a 1 or a 2 charge, and this is the cupric, it's the 2 plus charge. And the bromate, well, bromate has got a 1 minus charge. So which one am I going to need 2 of to make this work? Copper's got 2 covered by itself. The bromate, I need to double up on that. So Cu, open parentheses, 2 BrO3, close parentheses. All right. Calcium hydroxide. Hydroxide? Remember, that's just water that lost an H+. So calcium is 2 plus. I'm going to need 2 of those OH1 minuses. Put them in parentheses. You got Ca, open parentheses, OH, close parentheses, 2 minus, no charge, because I canceled out all the charge. 10 phosphite. That's a tough one. Okay, 10 phosphite. 10 is SN, right? Stannum is the old name. So 10,2 is going to be SN2 plus. Phosphite, though, is going to have a 3 minus charge because phosphorus forms a 3 minus charge. It's the smaller one of 4 and 3 oxygens. It's the one with 3 oxygens. So the phosphite is PO3, 3 minus, and I want to team that up with SN2 plus. Again, smallest whole multiple of 2 plus and 3 minus is going to be 6. I'm going to need 3 of those 10s, 3 of the SNs, and I'm going to need how many of the phosphite? 2 in parentheses. How about ammonium carbonate? Carbonate has nothing to do with Han Solo, but carbonate is carbon with a bunch of oxygens around it. Ite is the small one. How many oxygens? 2. CO2, and what's the charge? Carbon, you got to remember, 2 minus. Ammonium ion, what's that look like? Is that NH3? No. NH3 is the neutral compound ammonia, but slap an H plus on it, NH4 plus. Now you got your ion. NH4 plus, and you're going to need 2 of them to balance off the 2 minus charge on the carbonate. Slap them together, and you've got NH4 in parentheses twice on a CO2. All right, I know these structures look kind of complicated, but just treat them like you treated the monatomic species, and you won't have any problems. You'll take a little bit getting used to that 8th and the ith, but it'll come pretty quick. And when in doubt on the charge, look at the element in the center. With the exception of carbon and nitrogen, which you knew were going to get complicated. All the others, the non-metal oxyions, have the same charge as the underlying monatomic ion, which you can read right off the periodic table. All right, that's the polyatomic ions. Let's talk about another class of compounds. So you can name these. We're going to play with acids. Acids are we're going to get into a lot more detail with acids later in the course. We'll just give you a brief intro here. So acids. First thing you should know about acids, they're like the ocean. Never turn your back on it. Never underestimate an acid. A weak acid can do Phantom of the Opera type stuff. It can burn through steel. A strong acid can be harmless. One of the strongest acids we know is stomach acid, but it's harmless when it's dilute. It's concentration that's dangerous with acids. That being the case, never underestimate an acid. Always treat acids like the ocean. Never turn your back on them. Be careful with acids wear gloves, wear goggles, be careful with them. Now, when we talked about the compound HBr, I told you its name was hydrogen bromide. And I didn't lie to you. HBr is hydrogen bromide. And hydrogen bromide is not an acid. But it can make a unique kind of acid. There are some acids that are not substances, they are mixtures. Mixtures of two different materials that produce a solution with acidic properties. HBr, HCl, HF, and HI all produce the binary acids hydroiodic acid, hydrobromic acid, hydrochloric acid, and hydrofluoric acid. Now these acids, unlike the other acids that we will explore, are not pure compounds. They are mixtures of these substances with another substance. And as a hint, hydrobromic acid, what do you think the other substance is? You are correct. It's water. So HBr is not an acid, but HBr in water is an acid. Now, all the properties of an acid come out when you bubble HCl through water. The way we write the formula for these then, the way we distinguish between the HCl, the compound, and HCl, the hydrochloric acid, is we use the suffix AQ in parentheses to indicate it's in water, which now it becomes an acid. So if somebody asks you for the formula for hydrochloric acid, the formula is HCl, AQ in parentheses after. The AQ can be as a subscript or on full size. Either one is fine. All right, but HF is not. Hydrogen bromide is HBr. Hydrobromic acid is HBr aqueous. Hydroiodic acid is HI with AQ in parentheses. And HF, not an acid, but it can make an acidic solution by bubbling it through water. And when you bubble hydrogen fluoride through water, you can get hydrofluoric acid. HCl, on the other hand, HCl-AQ is hydrochloric acid. And again, that's actually stomach acid. Again, with acids, it's concentration that makes it dangerous. Strong acid or weak acid, they can sneak up on you. But when you have concentrated acid, that's when it becomes dangerous. All right, so those are the binary acids. And like I said, binary acids are unique in that they require that AQ. Not all acids are that way. In fact, most acids are just neutral substances that can break off and give you an H+, that can demonstrate all the properties of acids. You can make mini acids by putting a proton, by putting an H+ on the oxyions that we just talked about. So for example, if I take the sulfate ion and I stick an H+ on it, remember sulfate is SO4 2-. If I stick one H+ on it, okay, it's still not an acid. That's a hydroion. That's hydrosulfate ion. Hydrogen sulfate ion. But if I stick a second H+ on it, H2SO4 neutral, now it becomes an acid called sulfuric acid. And this one's a bear. This is one of the more dangerous acids. If I do that trick with PO4, PO4 3-, if I stick one H+ on it, I get a new ion that I can use, a polyatomic ion that's the same polyatomic ion I had before, just with an H+ stuck onto it. That's the hydrogen phosphate ion. And the formula is HPO4 2-, because the H+ neutralized one of the negative charges. If I stick a second hydrogen ion on it, it still isn't the acid. It's H2PO4 1-, and that I need to differentiate it from hydrogen phosphate ion. That one's got two hydrogens on it. That is the dihydrogen phosphate ion. If If I add a third one onto it though, now I form a substance that pure and by itself, H3PO4 neutral, that substance is phosphoric acid. And I can do the same trick with nitrate ion to form nitric acid. Or I can stick on a H plus on the chlorate ion to form the chloric acid, not to be confused with hydrochloric acid. Hydro meaning water, the binary acid. This is just HClO3. All right, there's a couple other common names that you need to be aware of. You're not going to be held responsible for them, but you're going to run into them. When you make the carbonate ion and add an H plus, you form HCO3 1 minus. That's the bicarbonate ion. The proper name is the hydrogen carbonate ion, and that's what you'll be held responsible for. But you'll hear bicarbonate all the time. You can do the same trick with the sulfate. HSO4 1 minus is the hydrogen sulfate ion, but if you there's a common name for it, bisulfate ion, and you can do it bisulfite and bicarbonate also. That being said, these common names you're not going to be held responsible for, but you may run into them in the laboratory, so you should be aware they exist. They're just shortcuts for the hydrogen carbonate ion or the hydrogen sulfite ion. All right. So we can make compounds from these polyatomic ions, these hydrogen polyatomic ions too. So if I take, if I want to write the formula for the hydrogen sulfate ion, I just slap H plus on the sulfate ion. Sulfate ion is SO4 3 minus. Slap an H plus on it, and it is H SO4 1 minus. And if I take slap it on the phosphorus, then I've got HPO4 2 minus, the hydrogen phosphate ion. If I put one on the phosphite ion, it's just hydrogen phosphite ion. And again, I can use these ions just like I use the chloride ion or the phosphate ion. These hydrogen phosphate ions can be used to form pseudo-binary compounds. If I take HCO3 1 minus, that is the hydrogen carbonate ion, also known as the bicarbonate ion. And if I team up something like the hydrogen sulfate ion with potassium, then the formula is just KHSO4. If I take the lithium and I team it up with the dihydrogen phosphite ion, then it is lithium. That's the plus half, and the minus half is H2PO3 1 minus, but the lithium cancels it. Now it's lithium H2PO3. You can also form, for example, magnesium hydrogen phosphate, and you can also form sodium dihydrogen phosphate. What's that next one called, where I got a lithium HSO3? SO3 is the small one, the sulfite ion. Hydrogen on it is the hydrogen sulfite. Slap it on lithium and it becomes lithium hydrogen sulfite. By the way, you notice I started at the end and worked my way forward from there. That's a useful trick, because that oxyion in the center, that's really controlling the whole piece. And that last one, NaHCO3, that one is the hydrogen carbonate ion with sodium, sodium hydrogen carbonate, also known as sodium bicarbonate, also known as baking soda. All right. So these are the compounds. And like I said, if you keep adding the H plus to it, you go straight to the acid. If I have, take that oxyion of the phosphate, phosphate's got a 3 minus, if I add 3 hydrogens to it, it turns into an acid. The phosphate ion becomes the phosphoric acid. The phosphite ion becomes the phosphorus acid. Same as when we were talking using ic and us before. the ik is the big one. So the 8 becomes the ik, and the eit becomes the us. 8 is bigger, mites are small. Ik is bigger than us because 2 is us and 3 is a crowd. Ik is the bigger one. All right, sulfate becomes sulfuric acid. And if I slap hydrogens on the sulfite ion, I get the sulfurous acid. I can form the per-bromous acid. I can form the hypochlorous, the per-bromate ion becomes the per-bromic acid, and the hypochlorite ion becomes the hypochlorous acid. 8 becomes ik, eit becomes us each time. All right, so for example, that first one there, what's that called? PO4, that's the big one. That's the phosphate ion. And I loaded it up with H pluses. I needed 3 of them to offset that 3 minus. That's phosphoric acid. And next one is H2SO3. SO3 is the small sulfur. Remember, sulfur and phosphorus are 3 or 4 oxygens. Everything else is 2 or 3. But phosphorus and sulfur are 4 or 3 oxygens. That's the small one. That's the sulfite ion. And the sulfite ion forms the sulfurous acid. HClO3, that's the chlorate ion. Chlorate ion forms the ic acid. That's the chloric acid. Don't confuse it with the hydrochloric acid. That's HCl aqueous. Whole different game when you're playing with the binary acids. But I can take that chloric acid and slap one more oxygen on it. Chloric acid is the biggest. You can have bigger than the biggest. That's the supersized one. What's that acid called? That's the perchloric acid. How about nitric acid? What's the formula for nitric acid? Nitric, that's going to be the big one. Nitrogen. Nitrogen is 2 or 3, so the big one there is going to be H and O3. Because remember, nitrogen's got a 1 minus charge, so only a single hydrogen on it. The carbonous acid, though, carbonous is from the carbonite ion. That's the smaller of the 2 or 3. So that's CO2, and carbon has a 2 minus charge. So to make an acid of it, I need 2 H pluses. Carbonous acid, H2, CO2. Sulfuric acid, and this is one you are going to run into a lot. Sulfuric acid has the sulfate ion in its center. SO4, 2 minus. Therefore, you're going to need 2 hydrogens to balance it out. Sulfuric acid is H2SO4. And bromic acid, again, bromic is the bigger of the bromine ones. That's BrO3. Slap 1 H plus on it because bromine has a 1 minus charge. Therefore, bromate ion has a 1 minus. Therefore, you'll need 1 hydrogen to make the acid. HBrO3. All right. That's all we got for now. That's naming polyatomic ions and compounds made from polyatomic ions. And then going on to talk about acids and understanding both binary acids, the ones that need the AQ. There's only 4 of them. And oxyacids. You don't need the AQ. Yes, they can be in water. Yes, you can use the AQ, but they're acids either way. These are the names and formulas we're going to be needing for in the next chapter as we get deeper into all this. I'll let you go. Have a good night.